One of the goals of Chapter 1 is to lay a more rigorous mathematical foundation for what we're going to talk about for the rest of the course. When we talked in introductory physics, we really kind of didn't get real rigorous with a lot of the mathematics. So we have to come up with the language of how we're going to talk about these things. So the first thing we really need to talk about is how do we represent physical things using mathematics. For example, in intro physics, when we talked about something like the mass or the temperature, these were examples of scalars, which only has a magnitude and no other information, and this we represented by a single number. When we talked about things like position or velocity, acceleration or forces, these we called vectors. And vectors have magnitude and direction, and typically when we represented a vector, say the velocity v, we would use three numbers if you're talking about a three-dimensional quantity. There were some more advanced topics, usually not covered in intro physics, but when we talk about something like the moment of inertia, we typically represented that as a 3x3 vector where these terms all represented the rotational inertia about different axes. Also, sometimes when you talk about things like the stresses and strains inside a fluid or solid, those required a 3x3 matrix. Now, any 3x3 matrix or any 1x3 vector does not necessarily represent a physically meaningful quantity. So, what we need to do is figure out what the mathematical properties of scalars, vectors, and 3x3 matrices need to be for them to be physically meaningful. Now, before we get started, we need to distinguish between the thing itself and the representation of the thing. So what I mean is we need to distinguish between the notion of the velocity of an object and the representation of the velocity. Because if we'd chosen a different coordinate system, these values right here might have different representations. What this chapter is really going to look at is how we can transform from one particular representation to another. When I'm speaking about these things, I will refer to this as, say, the velocity, when strictly speaking, I should be calling that a representation of the velocity. So, as we said, the goal of this chapter is to lay out the mathematical groundwork for representing scalars and vectors by defining what a coordinate system is and how these properties, how the scalars and vectors transform between coordinate systems. If we were to use a simple Cartesian coordinate system where we have an x-axis, a y-axis, and a z-axis, if we stuck with Cartesian coordinates, then it would be really trivial to talk about transformation between the different coordinate systems. It turns out we're going to move beyond just the simple Cartesian, and we'll talk about things like cylindrical coordinate system or polar coordinate system, and we need to come up with transformation properties of these coordinate systems that define the geometry of the space. So, just to start off with, what are the transformation properties for a scalar? That's what section 1.2 really deals with. And so if we imagine that we have a point in space here and we measure the temperature at that point, let's say it's 300 Kelvin, and I have another coordinate system that's rotated relative to this coordinate system so that we'll call it the x prime axis has been rotated that way, the y prime is rotated that way, and we'll say that the z prime is still lying along the z-axis. I want to say, well, what is the temperature at this point in space in my new coordinate system? Well, a scalar shouldn't change just because the coordinate systems have changed. So, what we would say is that the temperature at some point x naught, y naught, z naught should be equal to the temperature at the same point in the transformed coordinate system, x naught prime, y naught prime, and z naught prime. Now, before we move forward, I do want to mention the notion of a tensor, because this term will come up again and again. I just want to say, what exactly is a tensor? Well, that's what we've been talking about. A tensor is nothing more than a physical property whose mathematical representation satisfies certain transformation properties. So, for example, a rank 0 tensor is a quantity that is invariant under coordinate changes. In other words, a scalar. So when we talk about a rank 0 tensor, that's nothing more than the scalar. A rank 1 tensor is a vector. So my scalar is, say, 300 Kelvin. A vector then might be my velocity. A rank 2 tensor is typically represented by a 3 by 3 or n by n matrix. So if we were looking at, say, the rotational inertia matrix, where I have a total of 9 different terms here, that would be an example of a rank 2 tensor. A rank 3 tensor would require an n by n by n matrix. In other words, a matrix that has 3 dimensions. The rank 2 has 2 dimensions. The rank 1 has 1 dimension. The rank 0, a single number, essentially has 0 dimensions.